Section 8.4. This section is what we call trig substitutions. It's, as a lot of these sort of more advanced integration techniques, it's just sort of, a way to sort of be clever and use trigonometry and write some of our nice like right triangle formulas, the SOHCAHTOA style formulas and the Pythagorean theorem, trying to kind of leverage all that stuff to help us deal with just various sort of integral forms that we haven't been able to necessarily deal with in general yet. And so these are going to involve some square roots in a way that kind of can be related back to right triangles. And so as soon as you get right triangles involved and the Pythagorean theorem, then you're also bringing in, right, all of our good trig stuff. So what I want to do first, just in kind of a quick, I think it'll just be this video, is I just want to sort of review the SOHCAHTOA trig setups and some of the other formulas we're going to kind of reference as we go through this. And actually, well, in any event, let's get started. So the first thing we have is just like, if you have a right triangle, oh gosh, all right, I'm gonna have to, it's trying to like only uncover a certain amount of stuff. There we go. We'll pretend you haven't seen that other little bit. Anyway, so here's sort of a generic right triangle. We're kind of picking what we call a perspective angle, theta, sort of down here in the corner. We have our kind of side lengths, A, B, C, right? A and B sort of generically are what we would think of as the short sides, meaning that C is the long side. Out of that, of course, we get our good Pythagorean theorem. So A squared plus B squared is C squared. So the side lengths in the right triangle always will have that relationship. Also, the side lengths, we can sort of label them more specifically the opposite, the adjacent, and the hypotenuse relative to their sort of position with this perspective angle, right? So the opposite is the side that's across from our perspective angle, right? So the opposite is sort of across from the angle is here. The adjacent is the one that's sort of next door to that, and the hypotenuse is the long side, right? The longest side is always the hypotenuse, then kind of the opposite is across, and then the adjacent is the one that's sort of next door and is touching the angle, but is not the hypotenuse. From those definitions, right, those side lengths, we're sort of going way back to some of our original trig definitions. I guess I'll just cover all three of these, right? So we have what we usually call the sort of SOHCAHTOA definitions. So that is, right, sine function is going to be whatever the opposite is divided by the hypotenuse. So SOHCAHTOA SOH would be sine opposite hypotenuse, right? Cosine, CAH, cosine would be the adjacent over the hypotenuse, so it would be the adjacent here over the hypotenuse here. And then my tangent function would be the opposite over the adjacent, right? TOA, TOA, SOHCAHTOA. So tangent is the opposite over the adjacent. We then, of course, have our other three reciprocal trig functions, which is just sort of taking those formulas and flipping them, right? So cosecant is the same thing as 1 over the sine function, which means it's then just going to be this sort of fraction flip, the hypotenuse over the opposite. Secant is 1 over the cosine, so that means it would be the hypotenuse over the adjacent. And then cotangent would be 1 over the tangent, right? So that would be the adjacent over the opposite. So we have all of those definitions, right? Those are our sort of main trig definitions relative to this triangle picture. So keep all these in mind. We're going to sort of be using and referencing these setups kind of over and over again in this section as we sort of do these problems. So all this SOHCAHTOA stuff and the way these are set up is super important to kind of have at the ready. The other stuff we're going to use, we're going to recycle some of the same formulas that we were using in the last section in 8.3. So I kind of just rewrote them here so you have them just in your notes on one page. So this is our kind of our Pythagorean identity, sine squared plus cosine squared of theta, right, as long as these angles match, would be equal to 1. That means then, right, sine squared could be written as 1 minus cosine squared, and vice versa. Cosine squared could be written as 1 minus sine squared. There's versions of this also for secant and tangent. Essentially, if you take this and you divide everything by cosine squared, what happens is you get on here, 1 over cosine squared would be secant squared. Sine over cosine is tangent. Cosine over cosine is 1. So you get a version of this with secant squared equal to tangent squared plus 1. And then if you take that and solve it for tangent instead, just subtract the 1. Tangent squared would be equal to secant squared minus 1. Right? So that's all stuff that we were using in 8.3. We also used, oh gosh, what did we call these? The half angle formulas. So sine squared is the same thing as 1 minus the cosine of 2 theta over 2, and cosine squared theta is 1 plus the cosine of 2 theta over 2. So you can get from a sine or a cosine squared down to sort of a single cosine, but part of what happens is it doubles the angle. So we use all that stuff trying to help us find various integrals with combinations of secant, tangent, or like sines and cosines. Right, we had to use all those things. The only thing that's sort of new that I want to add to our list is sort of a reversed version of these types of formulas. So if this is a half angle formula, I guess we would call this a double angle formula. So meaning if you have the sine of 2 theta, it's going to be equal to 2 times the sine of theta times the cosine of theta. There are also a couple different versions for like cosine of 2 theta, but believe it or not, I don't think we're actually going to need or use them. I think this is the only one we'll need. If it ends up that we need that cosine of 2 theta, then of course I'll go back and put it in. Oh, one other thing I almost forgot. Did forget when I wrote this out. What color didn't we use that? Well, green. The other thing that's true that we could end up using, it's kind of an extension of this, but it's the idea that your tangent function can be written in terms of sine and cosine. So tangent of theta would be the same thing as sine over cosine. So if you get this kind of fraction, you can write it as a tangent, or vice versa. And then kind of by extension, right, that must mean that cotangent would be the reciprocal, would look like cosine over sine of theta. Try to just squeeze all this stuff in here. So that's a lot of trig stuff. We'll kind of pick and choose where we use this kind of as needed. But I would sort of have this formula or version of it, this sort of formula sheet handy when you're going through all these problems. Part of what's going to happen is we're going to be sort of doing these substitutions and translations. We're going to end up with a lot of different integrals in terms of like sine and cosine again, and secant and tangent in theory, right? So it's kind of an extension of what was happening in 8.3, but the forms that we get aren't really necessarily going to fit into the nice 8.3 forms that we have already. We could get, sines over cosines. We could get tangents over secants. We could get a lot of different things. So part of what we're maybe going to need to do is use some of these formulas to kind of simplify and clean up the different integrals we have to try to give ourselves a shot at integrating it. In any event, that's all sort of coming up. This is kind of just like the prelude. This is just the information we need before we can get started. All right, so we'll get started on this officially in the next video.